I am pleased to have the opportunity to present some of the work we've been doing at the University of Brescia as part of the Safe AgroBee project. Our role in this project has been to develop new tools that could help beekeepers make more informed decisions and support sustainable beekeeping practices. Specifically, we have developed two tools, an individual-based model and a health status index. These tools aim to help beekeepers better understand their hives, their surrounding environment, and how various factors interact to affect colony health and productivity. The first tool is the individual-based model, and it simulates the inner workings of a beehive. It tracks the hive's population dynamics, honey and bee bread production, and how these are influenced by the landscape and other pollinator species. Additionally, the model can simulate the action taken by the beekeeper, such as honey collection or supplemental feeding, and how external factors like weather impact the hive. There are several potential applications of this model. First, it could be used to estimate the carrying capacity of a given landscape, meaning how many hives can be placed in a specific area without exhausting local resources or completing too much with the wild pollinators. This is important for determining the optimal number of hives that a beekeeper can manage in a location without negatively impacting both their hives and the environment. The model also estimates the pollination efficiency of a hive, or how much a colony contributes to the pollination of crops and natural vegetation. This could be very useful in areas where crop production relies heavily on honeybee pollination, helping beekeepers and farmers plan more effectively. Furthermore, the model could be used to assess the resilience of an agroecosystem, particularly under different scenarios like changing resource availability and climate conditions. This could provide valuable insights for long-term planning, especially in light of climate change, which we know can significantly impact both bee health and agricultural production. The results we obtained through the model have provided important insights. For example, we found that the nectar often acts as a limiting resource for bees in the locations we studied, whereas pollen is generally more abundant. This reflects the common practices of the beekeepers, supplementing hives with sugar but not protein during periods of dearth in the locations we studied. The model also demonstrated how varying landscapes types can affect the pollination demand and how much honey bees contributed to fulfilling the demand. In some areas, honeybees play a more critical role than in others, highlighting the importance of location when managing the hives. Additionally, we use the model to estimate the annual productivity of colonies, both in terms of the amount of honey and bee bread produced and the honey that can be harvested by the beekeeper in a year. The results emphasize how different locations can influence hive productivity, allowing beekeepers to better plan their management strategies based on specific characteristics of their environment. The second tool, which is the Health Status Index, is based on structural equation modeling, which is a statistical methodology that allows the model to model emerging properties not directly measurable in a system. It is designed to simplify the complex interactions that affect hive health into a single, easy-to-understand value. The Health Status Index takes into account multiple factors, including environmental conditions and the beekeeper's own management practices, to provide a comprehensive view of colony health. By summarizing all of these variables, the Health Status Index could help beekeepers assess the overall health of individual colonies and compare them with others. It could also track the health of a colony over time, allowing for early detection of problems and enabling timely intervention before major issues arise. The results of the status index have shown that landscapes with higher productivity generally lead to healthier hives. However, the composition and proximity of different plant species are also important. The type and distance of crops or wild vegetation near the hives can significantly influence colony health, emphasizing the need to consider not just the quantity of resources, but also their quality and location respective to the hive. The status index also allowed us to explore the impact of biotic stressors having an effect on queen fecundity, larval and adult mortality, and resource consumption in the hive. The results indicate that the higher the stress levels, the lower the overall health of the colony. Finally, the status index highlighted the seasonal fluctuations in hive health, with the availability of resources in the landscape during the flowering seasons being a key driver. This means that beekeepers could use this tool to monitor health throughout the year and respond quickly to any drops in colony performance. In conclusion, these two tools, the individual-based model and the health status index, offer a wealth of potential for helping beekeepers make data-driven decisions. By using these models, beekeepers could gain a deeper understanding of the interactions between their hives and the surrounding environment, allowing for more precise management strategies. Whether it's deciding how many hives placed in a location, predicting colony production, or monitoring colony health, these tools could provide valuable insights that lead to better outcomes for both beekeepers and the ecosystem they work in. As we move forward, it is clear that these kind of models will play an increasingly important role in promoting sustainable beekeeping, ensuring that we can continue to protect and support honeybee population while balancing the needs of our agricultural landscapes. Thank you for your attention.